quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
Hi, I'm Russell Leidig. It's July 1, 2014. This is a discussion about pilot wave theory, more formally known as the de Broglie-Bohm interpretation, versus the Copenhagen interpretation of quantum mechanics. It assumes that if you're not familiar with these matters already, that you've looked at Nick Herbert's page on Bell's theorem and his very efficient proof thereof, and his explorations of John Clauser's experiments on the subject, which is all linked in the YouTube description, and also the fantastic article by Natalie Walchover over at Wired.com about investigations of classical pilot waves. So in this particular experiment, which I think can maybe tell the difference between whether the Copenhagen interpretation or the pilot wave theory is the better model of reality, we have a twin photon source, and this twin photon source is ejecting photons of the same polarization, that is either both vertical or both horizontal in opposite directions. And so initially we have Bob's detector at 0 degrees and Alice's detector at 0 degrees, so that when a vertical photon shows up over here, another vertical photon shows up here, and the same thing for horizontal. So the vertical photons will pass through the detector, leading to a binary 1, and the horizontal photons will be blocked by the detector, leading to a binary 0. Now, the Copenhagen interpretation essentially says that photons in stream A and stream B do not actually know whether they're going to pass through or be blocked by the polarizing filter until one of them hits a polarizing filter. So these orange distances here are not necessarily exactly equal. In fact, they could be quite different. But basically, the wave function will collapse as soon as a photon in either stream hits either detector. And immediately at that point, no matter what this length L is between the detectors, the other photon will know whether it needs to pass through the polarizing filter or be blocked by it in order to maintain consistency. So the pilot wave theory is a little bit different. It says that after you turn this photon source on and you emit, say, 100 or maybe 1,000 photons in opposite directions, space itself essentially develops a memory. There develops, for lack of a better term, a standing probability wave between the detectors that is really the memory of previous photon trajectories, which influences future photon trajectories. And specifically, it influences them in such a way that the long-term statistics of this system are consistent with the predictions of the Copenhagen interpretation. So for systems with static topology, like for instance, if we screw this detector down here onto the table, and we screw down this detector, they're both at 0 degrees, then the pilot wave will rapidly form between and in fact beyond the detectors, and will govern everything so that we get just what we would expect to get from the Copenhagen interpretation. And so to the extent that we're talking about static topology in the laboratory, basically these are one and the same theory. But I think the differences can be shown if we're able to introduce an element of dynamism in a particular way that exploits a difference between the theories. Let me explain this a little bit. So basically, Alice's detector chooses randomly between 0 or 90 degrees every time t. So every time t, there's some computer that decides whether we should have the filter in a vertical or a horizontal orientation. And by the way, of course, this is all in a plane that's perpendicular to the photon stream, as it is with Bob's detector on this side. And the key is that the time t has to be much, much less than the time that it would take light to traverse the distance L between the detectors. So now, how exactly does the choice of the orientation of Alice's polarizing filter occur? So this is a binary 1-0 decision. So where are the ones and zeros coming from? Well, they're coming from a distant galaxy or star, which is at least half the age of the universe. And the reason for that is because we want to make absolutely pedantically sure that there is no possible way that there's some kind of weird pilot wave that originated in a distant celestial object and interacted with the Earth back and forth a few times, so it set up some kind of predictable scenario. Basically, we want to ensure ourselves that absolutely new information is coming into Alice's digital optical telescope here. Now, if Alice spills some coffee on the telescope and we get influenced by local phenomena, that's fine. We just need to make sure that some of the information is truly new to the system. And this information is then digitized into probably red, green, and blue pixels. And by the way, there's no lossful image compression allowed. So we take the absolute raw data and we mail it off to this computer, which is Alice's random bit generator. And all this thing does is it XORs all of the ones together in this giant image, and that means that if there's an odd number of ones, the result will be 1. If there's an even number of ones, the result will be 0. So what we have is essentially a highly unbiased random bit that gets ejected to this polarization rotator device. And what this device does is it simply selects between 0 and 90 degrees. And if we're not in the correct state, then it rotates the polarizing film into that orientation. And this is conceptually a mechanical process, but perhaps it could be an electrical process involving an optically active crystal that can change its preferred light polarization based on the application of some voltage. So the time that it takes between receiving the last photon, which ultimately will make deterministic the bit that's ejected into the unbiased random bit stream. So in other words, from the time that the last photon comes in that could actually change this 1 or 0, until the actual rotation is completely finished, if in fact the rotation needs to occur, that whole transition time has to be less than the time t. And again, remember, the time t itself is much, much less than the time that light would take to migrate across this distance L. Okay? So here's Alice's detector angle. It's alternating kind of randomly between 0 and 90 degrees, and there are these very brief periods of transition. I've actually exaggerated this somewhat. The transition is very, very quick. And this is a single period time t, and all the rest of these troughs and peaks are multiples of time t. And during a single time t, thousands of photons are launched in either direction from the twin light source, so that we can get a really good statistical confidence in the error rate. And the error rate is simply, if you look back at Nick Herbert's page, it's just simply defined as the percentage of zeros and ones that disagree between Bob and Alice. So if basically, if their polarizers are in parallel, there should be 0% error. If they're 90 degrees apart, there should be 100% error. If the angle between them is somewhere between, then you're going to get an error percentage somewhere in between, which is governed by quantum mechanics. But so Bob actually is looking at Alice's detector, and maybe there's a red light on it that lights up only when it's at 90 degrees, so he can actually see what angle it's at. And the angle that he observes is actually delayed by what in pilot wave theory would be a pilot wave propagation delay, but in any event is simply a light delay, because Bob has to receive photons from Alice's apparatus to understand what the polarization is. So why does this matter? Well, maybe it doesn't. So quantum mechanics says that we can treat this whole thing as a series of John Clauser experiments, basically where if the polarization is 90 degrees, then we should expect 100% error. If the polarization is 0 degrees, we should expect 100% agreement. And we can basically have Alice save her series of 1s and 0s and Bob save his series of 1s and 0s, and we can compare them after the fact and verify that, when Alice was at 90 degrees, all the bits arrived opposite. When Alice was at 0 degrees, all the bits arrived equal. Well, that's not very exciting. And this occurs ostensibly because entanglement is an instantaneous affair. So as soon as Alice does something that is going to morph the probability of various 1s and 0s arriving on her side, then it has to have an instantaneous effect on what happens on Bob's side. But pilot wave theory says that the error rates are going to vary depending on Alice's detector angle and Bob's outdated perception thereof, because the pilot wave itself is no faster than light. So we're not allowing, unlike in John Clauser's experiment, and unlike in a conventional EPR scenario, we are not allowing the pilot wave to stabilize. So we have a chaotic pilot wave that's trying to stabilize itself, but it can't because the detector angle is changing much, much faster than the time it would take for the pilot wave to propagate the information about that detector angle to the other side. So in the pilot wave world, during this time period when Alice is at 90 degrees and Bob in fact Bob in fact thinks that Alice's angle is 90 degrees, then everything works out fine. We should get 100% error rate. So our predictions would work there, whichever theory is true. But down here, as far as Bob is concerned, Alice's detector is at 0 degrees, but in fact it's at 90 degrees. So there's some confusion, if you will, as to which way the photons should orient themselves when they impact both detectors. And I think what this amounts to essentially is a collapse of the wave function, such that the photons now become uncorrelated. But they're not supposed to. They're not supposed to if quantum mechanics is correct, because we haven't actually destroyed the entanglement. We've just simply we haven't changed the rules that say that when Alice's detector is at 90 degrees, Bob should observe the opposite. It's just that Bob has a wrong idea of the orientation of Alice's detector angle. So I think that you're going to see differences in error rate between pilot wave theory and quantum mechanics when this kind of discrepancy occurs. And namely, I think, and I'm not sure, but I think that if pilot wave theory is correct, you should get basically random noise during this time, 50% error. And of course, when they're in agreement, then you get exactly what's predicted by conventional quantum mechanics. But I don't know, because I don't know which theory is correct. So can someone please do this experiment? So here we have 3 mountains, X, Y, and Z, and there's a twin light source sort of in the middle. It doesn't have to be exactly in the middle, and it's shooting entangled photons towards Bob's detector and Alice's laboratory over here. And by the way, Alice is looking at a celestial object over in this direction, opposite Bob, so she can be assured that she receives information from that celestial object faster than Bob can be influenced by it. And we run this experiment and we see what happens. Now, we could also use fiber optics to do this, 1,000 kilometers of fiber optics or whatever. But if you do that, just make sure that you don't wind it up in a spool, because there is the remote possibility that information could escape through the side of the fiber optic waveguide, traverse across 3D space, and basically shortcut the whole thing, and then we wouldn't have a very definitive answer. But anyway, maybe I'm mistaken. Maybe the Dirac equations, for example, the relativistic equations of the Copenhagen interpretation actually imply that because Alice's detector is oscillating so rapidly, that this is not really a valid test of the John Clauser sort, and that the different rules apply, so you actually still cannot tell the difference between these theories. But maybe not. The only thing that I know for sure that the Dirac equations ensure is that particles themselves cannot travel faster than the speed of light. But maybe there's some other fundamental problem with this. If there is, please explain what's wrong with it in the comments. If, on the other hand, you think you can do this experiment, or if you do it, obviously, let us all know. But if you want to contact me, the comments are not the place to do that. Instead, please visit my blog at accelerationhorizon.blogspot.
laserpointers.com.
Hi, I'm Russell Leidig. It's July 1, 2014. This is a discussion about pilot wave theory, more formally known as the de Broglie-Bohm interpretation, versus the Copenhagen interpretation of quantum mechanics. It assumes that if you're not familiar with these matters already, that you've looked at Nick Herbert's page on Bell's theorem and his...
It was a particle or a wave. A laser shines a coherent beam of light through a film disc containing 2 parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers. Quantum
is very efficient proof thereof, and his explorations of John Clauser's experiments on the subject, which is all linked in the YouTube description, and also the fantastic article by Natalie Walchover over at Wired.com about investigations of classical pilot waves. So in this particular experiment, which I think can maybe tell the difference between
QuantumLaserPointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light...
Whether the Copenhagen interpretation or the pilot wave theory is the better model of reality. We have a twin photon source, and this twin photon source is ejecting photons of the same polarization, that is either both vertical or both horizontal in opposite directions. And so initially we have Bob's detector at 0 degrees and Alice's detector at 0 degrees, so that when a vertical photon shows up over here, another vertical photon shows up here, and the same thing for horizontal. So